I hope it's high dimensional, so I can do something with the high dimensional function. So what is the main talk? It's about adaptive approximations on partitions and some ways to generalize it for high dimensions. So I'll claim some results which are usually considered for low dimensions, but there is a way to go for high dimensions. So we consider some domain, and on this domain we want to approximate the function f, and we want to subdivide the domain in different parts, and in each of the parts to approximate with a polynomial. So the polynomials could be different. I'll consider some general polynomial space pi, but it could be done that pi depends on delta and actually varies for different cases. This is the HP approximation, but I will not consider this today. So as usual, this is the indicator function, and we want to analyze the algorithms that realize such an approximation in terms of complexity and convergence. And the main goal first would be to define what that means when we consider generic trees, and then to try to make a setup for the high dimensional case. So there are three basic types of adaptivity. I'll consider the H adaptivity, which decreases the size of the elements of the partition to achieve the better local approximation. We can do that with fixed partition and increase the number of the polynomials we're using. So in the polynomial space we're approximating, and HP adaptivity, which is for both. I actually will consider only H adaptivity, but I want to emphasize that HP adaptivity is also possible in this setup. So the general approach would be to increase the concentration of degrees of freedom when we want to better approximation in certain part of the domain. And actually the new results are about gradual change of the concentration of degrees of freedom, which is achieved by requiring conformity of the partition. So in general, we'll consider a function from x to y, and x is a domain equipped with some measure. We assume that the measure is 1. This is the probability measure. And we want to have adaptive binary partition of x. What that means, we take first the whole domain, then we subdivide it into two, then each of the parts we can subdivide in another two parts, and that practically builds a tree. And this tree, we want to decide whether to subdivide some portion or not, and that would be the adaptive decision tree. So we can consider this, the generic case would be the tree, but it could mean subdividing it to tetrahedra, as in this case, or subdividing the rectangle into small rectangles. So this tree encodes both, and we can imagine that this actually can encode very high dimension. So this is, the trees are dimensionless. If we want to put the dimension, that means that we should impose some additional properties which describe the approximation.
So wait a minute.
Yeah.
You're going too fast.
Okay.
So if you decide to subdivide, is the rule for subdivision set in advance?
Yes,
one of these possibilities.
No, we have one of these possibilities. So we have a domain. In this domain, we have a pre-described way of subdividing the domain.
Yeah.
However, we don't know where to subdivide. And this is what the tree describes. So these are the decisions made depending on f. or the information we get for F.
What I didn't understand is you say sometimes you use tetrahedra, sometimes
No,
you use
I want to say that regardless of how I subdivide, the algorithms would be the same, but the way to subdivide is set in advance. Okay? Good. So we have this approximation. Now we have the general approach to increase the degrees of freedom. That means we put more degrees of freedom on a certain space when we want better approximation there. And we want to define three algorithms. And for these three algorithms, we first have to call sometimes the elements of the tree. So if we have a tree, we have, this is the parent, these are the children, and then we can consider the children of the children, and so on. That should be, if it is a binary tree, it should be a full binary tree, because we cannot skip one of these elements if we want to have a real partition. So this we subdivide it into two, and then another two, and this is the C1, and this is C2 1 and C2 2. Say C2 1 and C2 2, and so on. We can get that. We want sometimes, in order to follow the geometry of the domain and geometry of the function, we want to have properties as conformity or grading. In triangulations, when we have a triangulation, we want to have, in general, not to have hanging nodes. Say we cannot allow this kind of thing. We have to make additional subdivisions in order to make conformity, or I'll have a slide later to explain the grading. And usually the complexity is measured of the number of the elements which we have. And what we want to discuss what is the best approximation. The best approximation is the approximation which follows these rules, have n elements at the end, and this and the difference between the norm is minimal. So this is the best approximation. We usually, in approximation theory, we define approximation classes, and which are the functions for which we have the rate of the approximation is n to some power. This is the rate optimality. However, we want to consider something more. We want to consider a near best approximation, in which we have that the difference, the error actually is C1 times the best approximation, but not with exactly the same n, which is here, but with slightly smaller number, because actually matching with the best n doesn't give us very good constants. So the target problems initially for this problem were numerical PDEs. In numerical PDEs, what we have actually we have some domain. After that we solve approximately the equation. We have, say, residual estimators, find out what are the local errors, and based on this we make a decision where to subdivide further. So we cannot return back. So we want to have nested spaces also. That means once we subdivide somewhere, we introduce already our degrees of freedom. We don't want to go back in this kind of approximation. And we have no other information of the function, so we make always a posterior decisions before the next refinement. And in this way, we want to define now the generic problem. We want to work only on trees, and first of all, we want to have a function for the error. That will not be the L2 error, that would be the square of L2 error usually, but we can put any LP error where p is between 0 and infinity. We cannot do that for p equals infinity because that is simply a maximum and it doesn't have this subadditivity property. The subadditivity property means when we subdivide a domain and add the errors there, we have the total error. So if we subdivide something into two, we want to have that the errors add together and give something smaller, because if we subdivide, we expect to improve the approximation. So in many cases, because we don't have exact error, we have estimates for the error. We usually have some equivalence with the constant C0. That's why sometimes it's better to consider weak subadditivity to account for this constant. So so this is an example which tells something about the greedy strategy, which is kind of the most natural strategy for such an approximation, which actually fails. So if we have the L infinity norm, probably that's the best we can do. But when we have integral norm, then we might fail. And here's the example. The example is the following. We have an interval, and in this interval we have some singularity. So we have an interval, we have some singularity here, which gives some big error. And then we have some small roughness in this case, in which we have to subdivide to some level. And then here the error would be b square all the ways here. And here would be, in this case, would be a square, which is bigger than b square. If we follow the greedy strategy, we'll continue to subdivide here up to the end of time, because capital N there is a very big constant, so we have to do a lot of subdivisions in order to resolve this error. However, if we subdivide each of them just once, we'll dismiss this error. So that means instead of having only the error, which is a square, which is the optimal, we'll have 2 to the k times b square, and b square is very close to a square. So that means we have a 2 to the negative k, a constant which we have to resolve. So if we cannot do the greedy strategy, we have to modify it somehow, because the greedy strategy is the way to get linear complexity, and therefore we want to have some modification. So in this modification, practically we'll use some way to account for this kind of phenomena when we subdivide too much in one direction and that there is no result. So this is the idea. This is from the paper with Ron in 2004. So the basic idea was the following. Each time we subdivide, we want to have some penalty, and we want to increase this penalty by 1. So how we introduce this penalty? By simply modifying the error in such a way that it becomes smaller. So if the error is smaller, we have to subdivide something else there. So and this is the way we achieve it. So a little bit later, just trying to improve it, on the constants, we change a little bit the function of that is again the penalty, but roughly speaking, we have this this way. Okay, I want to change it a little bit. So let's have 1 over the modified error is 1 over the error plus 1 over the modified error of the parent. And following this this approach, the adaptive tree algorithm is very simple. So what we do, we just use these modified errors and we subdivide whichever error is the largest. We can do that in a bulk, taking all the errors which are between 2 powers of 2 and do it faster. And based on this, we can prove the following: estimate that this algorithm using capital N elements of the partition performs as the best approximation for n elements with a constant with small n elements, and the constant is something like this. These are very small constants because if you take the small n to be 1/2 of the capital N, this constant becomes 2, and this is 1/2 of the capital N, so the constants are very small and very efficient. So how we can do that in n dimensions? So the first thing, when we are approximating point clouds, we have some points. And if we start subdividing in n dimension, you know that in order to decrease the size of the element 2 in each direction, that requires 2 to the d times subdivisions, which are too much if d is, say, 100 or more. So we did some methods which we called sparse occupancy trees. This is with Ron, Wolfgang, and Philipp Lamby. So we had 2 papers. One is for climate change. We actually processed the data, which was 220 dimensional. So that is, and achieved better results than the standard methods. So what is the basic way to do that? It's to start, so we assume that we have small n independent drawings identically distributed to the measure in the space X, and our hope actually is that this measure rho is not full dimensional, that it's actually spread around a manifold or some set of lower dimension, and we want to capture this set without actually resolving the set itself. We just want to have direct approximation approach. So I should say that Mauro Maggioni usually consider this one on manifolds, and he approximates the manifold and then approximates the function on it. So we want to do it directly. So how we do it directly? So we distribute the data on our tree. We have a binary tree. We consider in which places we have points. We wouldn't have points everywhere, because if we have 100-dimensional space and only, say, 1 million points, they obviously will not enter everywhere in the tree. And what we want to say which cells are occupied, and based on that we can have a full tree, which is looking like this, or we can have a sparse occupancy tree, which actually dismisses the small element. So how that is realized? It is realized with keywords. So each time we consider subdivision of the tree, we are having actually 2 bits, 0 or 1. And when we are doing that, each point has some bit stream which corresponds to the point itself. So we have different bit streams. You have to know that usually the precision which we are calculating the coordinates of the points is limited, so we don't have a lot of bits to spend. Say we could have 100 bits to spend or something like this for a point in a dimension, and then we can combine all these bits. And when we do that, we have something like this. This is only 5 bits, so there's only 14 points. But what we do, so the first split is here. So we have this part starts with 0, this part starts with 1. Then we have the next split, and then the next split, and so far. So we have an occupancy tree, which practically have different intervals after the points are ordered, and this actually processes a tree which is similar to what we have. But sometimes if we have just one point somewhere, we want to combine these points, and this is done here and here, and we have sparse occupancy tree when we ignore the places where we have low concentration of measure or just 1 point or a few points. So what we do, so basically the idea is the following. So after having these points distributed, we can consider to apply learning theory algorithms for that, and these learning theory algorithms, they consider in each element of the partition. So we assume that we have some partition. I'll tell you how to calculate this partition a little bit later. But in this partition, we want to have some substantial measure. If we don't have enough measure, we cannot have learning theory estimates for that. We did that with a paper with Albert, Wolfgang, Ron, and Volodya. And in this one, we have piecewise constant approximations, and we consider that if we have such an approximation, we have some estimates about the function, and this practically says the following, that we cannot have so for the exact measure for this, but if we perturb the measure a little bit, we can prove that based on the estimates of the so what we do, we practically consider the tree. When we consider the tree, on each element we consider whether the measure is bigger than delta or not. So we cannot do that for practical reasons. From the data we cannot get that, but we can have a slightly bigger than, so if we consider the numerical measure based on the sample Z, and we have 4 delta over 3, then with high probability we can say that in this case, if this is the tree we are building with this threshold, this tree would be between the actual tree with 2 delta and delta measures with high probability. So basically that means we are building a tree based on the data, and after we have the tree, we can actually apply the tree algorithm to it and have the near best approximation on this tree and have the approximation there. So this is this, however, have if we apply sparse occupancy tree directly to that, so this is one phenomenon which when we have some concentration of measure somewhere here, so in this place, and then just some residual measure around. If we do that directly, it could happen that actually in the nearby, so this is, the measure is not exactly 0, this is slightly positive there. So it could happen that when we're zooming in, although it is concentrated here, the measure in the blue part is bigger than delta. So we have to build it on chunks because we actually have a monotonicity in this shrinking the domain. We can actually identify the regions in which the delta is, say, around 4/3. That means between delta and 2 delta, and then consider further what to do with that. So these results, we actually have an implementation. We consider this kind of approximation because this is piecewise constant approximation. It doesn't give very good results. In order to do a little bit better, we have to try to have some piecewise linear, or at least to relate that to piecewise linear approximation in order to achieve better results. So this one, we have this for the piecewise constant approximation. If we want to extend it to piecewise linear, what we have to do, we have to consider all these structures to try to connect to some vertices and to mimic the piecewise linear approximation. So, and then the next thing is, why don't we practically go for piecewise linear approximation and do something about it? So in order to do that, we need conforming partitions. So what are the conforming partitions? We try to subdivide the domain. Here it is done in 2D because this is the original method for the newest vertex bisection. What we have a domain in which for each triangle we have identified the newest vertex in such a way that the edge opposite to the newest vertex is shared by the two triangles and both of them point to the edge. So this edges has to be subdivided. After some subdivision, we can enforce, say if we want to subdivide this place here, we have 1, 2 subdivisions, and then we have to enforce some further subdivisions based on the rules to have a conformity. So this is pretty well understood, and there are several results for adaptive finite element methods for optimal convergence rates using this methodology. The basic property is that the approximation spaces are nested in this approximation. So we don't have to say before that it was the red-green refinement which has not nested spaces. In addition, it allows extension to d-dimension, which I'll discuss a little bit further. First, let me say that this is a conforming mesh. This is somewhere we have some concentration, so some singularities here. That's why we want to concentrate the degrees of freedom in this part. This is the alternative way when we do the dyadic subdivision. So instead of doing binary subdivision, we can consider hypercubes and divide each into to the d elements. However, in order to have monotonicity of the some gradedness of the distribution of degrees of freedom, we don't allow more than one hanging vertex around the cube. So you can imagine this is in d dimension, and these are cubes, and this is the grading. The results I'm talking about, they apply to both type of partitions. So how we can improve the partition, how we can make it to move slowly. So the basic idea is the following. So if we want to define a piecewise linear approximation in d dimensions, we probably, the easiest way people think about it is to use deep neural networks and ReLU. So the ReLU gives exactly piecewise linear continuous approximation, but in so many elements that it cannot be controlled, and okay, I don't know what to do, but probably close. No, but yeah, okay. So we'll see. So in this case, however, we want to control the approximation. We want to have very few degrees of freedom and want to be as good as possible. So we had this theorem with in proving the adaptive finite elements, in which we actually prove that when we mark some elements for subdivisions, we can complete the triangulation so it becomes conforming. In this constant, however, in 2 dimensions is 14, the constant of equivalence of the marked elements and the final elements. And then Rob Stevenson did that in 2007 for general D dimensions where the constant is much worse. So so we want to do something better, in a sense, to have an algorithm which doesn't mark it, subdivide it, always keep conforming triangulations. So the basic idea is to do the so-called real-time optimality adapting mesh, which is used in computer graphics in order to have these nested partitions back and forth in a very fast way. So based on this idea, we decided to change the approximation. We actually consider best approximation on conforming partition with the same thing. N is the number of the elements, and we want to see how to modify the algorithm so that works. And this is joint work with Francesca, Fierro, and Andreas Veeser from Milan. And this is the basic idea. So we have a primary tree, how we subdivide a triangle. We first subdivide here, then there, and so on. But we want to introduce a secondary tree. The secondary tree says the following. If we want to subdivide this triangle, say, this green triangle, we first have to subdivide the blue triangle. Because otherwise we'll leave a hanging note. We have to subdivide this here and then to complete there. So in a sense, we have a tree in which says if we want to subdivide this triangle, we have to go subdivide this too. So this looks like this if we have 14 levels. Of course, this is unrealistic because here, if we want to subdivide this triangle, we have to already subdivide the green one. But the next picture shows, actually the next one, shows something. If we want to subdivide any edge in this triangulation, we first have to subdivide this green one. So that means if we want to subdivide, say here, we have to go subdivide this one first, then this one first, and this one first, and then we go and subdivide these edges. So practically that means that we have a tree of edges in which this is a parent, these are the children from one side, and these are the children from another side. Keep in mind that we have to, oops, get a subdivision. Now oops. Okay. I probably want to, I put the power on, but it was off for some reason. I'll draw something, I'll explain a little bit later what that is. Okay, thank you. Okay, I'll explain what that is later. I'll need that. Okay, so how the algorithm for conforming partition looks like is the same as before. However, the rules change in the game. So what we have is the following. We have a triangulation. In this triangulation, we have this modified error, which calculated somehow, and then we see that somewhere the modified error is the biggest, and we decide to mark this cell. However, instead of the usual way to subdivide this cell, we don't subdivide it. We subdivide the one, say this is the cell we decided to mark, and that means we subdivide the green one, because that is the one which shows the secondary tree where to subdivide. So we mark in one place, subdivide in the other, and then, however, instead of punishing where we subdivide, we punish where we mark. So we put a penalty on the marked cells, so that means we increase the subdivision there. This doesn't sound a very good idea, but the proofs work. And we actually prove the estimate, which is almost like the previous one, just a factor 2 worse for the best approximation on conforming partitions. And the good thing is that we have fairly good results, and that is what so we have a function, and this function looks something like this. It is two-dimensional. It looks like that because we consider this is from negative delta to delta. So that is the profile. It is two-dimensional function, so this is the profile everywhere like that. And this one, what is happening, because we are we are considering the H1 semi-norm for the function, we practically want to approximate a function which is 0, then has a linear part here, and then it's 0 again. These are the gradients. In one direction, in the other direction is the same, so we don't draw them. And then we want to subdivide this with piecewise constant functions. So practically we want to have some subdivision like this. That means to decrease the error we have to go there. But then there is a big dependence. Where is this delta? If this delta is here, where we have to subdivide next, then we'll have no error here. But if it is somewhere in between, this is a huge, so if we try to approximate this type here, we'll have a huge error. And you can see from the next slide what are the results. This is when the delta is 1/2, that means it's exactly on the grid, and that doesn't create a lot of error. So the one with the grading is the same, but here is the difference when we have that the jump is not on the grid, and when it is not on the grid it doesn't resolve itself, and the error here is about 7-8 times smaller, so that goes very fast and very well. So in order to do that for n dimensions, so I'll go for the nearest vertex bisection for the high dimensional way. So that goes in the following way. We have this the standard simplex. It has these coordinates, and then we usually do the following. We choose the first and the last. We define a new point, which is kind of split this edge into two. Then we choose, we split into two simplices, and in that, the next step we choose this pair or this pair, and so on. We continue. In fact, it is in each dyadic level we have different ways of splitting, and in each way of splitting we have the vertices of the new simplices look like this, and the interesting part is that this is the last slide, and the vertices, the splitting, in fact, when we are splitting simplices, we're splitting an edge. And these edges, if we have to split one edge before the other, we call it parent. And the interesting part is that we have that for the first splitting edge, it has d parent edges. The next one has only 2, then 4, until 2d times minus 2, and then we go back again. The good thing about 2D is that we have only 2 and 2, which exactly meets with the two trees. One is the subdivision tree, and one is the primary tree and the secondary tree. But here we cannot have trees, because if we subtract 1, we never had just one parent. So we have some graph. in this graph, we have O of n times n, so we can employ the same strategy for subdivision, which means that we mark a cell for subdivision, but we subdivide somewhere else one of the ancestors which are further away from this tree, and that is easy to track. It's about d times n instead of 2 to the d times n elements, and that can be done. Thank you very much.
Okay, we're eating into coffee a little bit, so but let's take a question or two if you have any questions. So, in the end, I mean, did you improve on Rod Stevenson's constants and
Oh yeah.
generating? Okay, so what is the conclusion?
No, the conclusion is practically.
Improvement in constants.
No, the thing is that actually algorithms perform much better numerically. This is even for this simple case, which I described. We have that when we do we work on conforming partition, we actually distribute the degrees of freedom much better than when we're doing this mark reform.
A theorem with a constant that says
Yes.
something?
Yeah, and that is.
Is that the d and 2 to the d, or is that no?
No, this is for in
That
general.
I understand, but okay.
For that, it's for general trees. I haven't done the experiments with higher D to see how that will perform. In a sense, the problem is the organization of data there. It's possible to do it, but how to do it, it's...
Anybody else want to shout in? No. Okay. So now we're going to have coffee. What time does the next session begin?
In 20...
3:40? Do you want to make it
3:40.
3:45 to give them a little bit more time, or leave it at 3:40?
No, 3:40 is okay.
Okay, 3:40,
Okay.
next call.
Okay.